University of Ebolowa, and he will talk about collective behaviors in neural networks, a recurrent topic in our event. So, Gaël, please.
Okay. Thank you for giving me the floor. And also thank you for inviting me. Like he said, I'm Simo Gaël Rosain from the University of Ebolowa in Cameroon. The topic under which I'm going to speak to you is entitled Collective Behavior in the neuronal networks under the action of electric and magnetic fields. So, to set the scene, it is important to present the context and motivation of our works. Without losing time, let us say that we note that the understanding on control of mechanism linked to memory is remain important in the world of science, and in addition, the existence of neurodegenerative diseases such as Alzheimer, epilepsy, schizophrenia is also more important in the world of science today. We also know that we live in an environment battered in electromagnetic fields having several sources like a high voltage line of electric cable, radio and TV transmission antenna, and gadgets such as cell, radio, and welding station, and also microwave ovens. So, as motivations, we can say that the brain is a building block of many neurons, and neuron is a cell. Neuron is a nerve cell, which is a nonlinear element. No, it's nerve cell which is a nonlinear element. And just yesterday, the Estadao website published that the scientists create large map of human connection, and discover unexplainable phenomena. So, according to them, researchers from Harvard and Google has implemented a neuronal from a brain in a map of 57,000 cells with 115 million connections. So with 115 million synaptics. So this information reinforces the idea of this workshop also, because here we are trying to understand the process on dynamical, the dynamical process on complex networks. Neuronal synchronization is linked to several disease. Is also linked to several behavior in nervous systems, and this phenomenon is also linked to several diseases like Parkinson and so on. The existence of neural synchronization of synchronization and asynchronization in a given population materialize what we call chimera state. And chimera state, for its part, is also analogous to many cerebral phenomena of aquatic mammal and some birds, which when they live, a part, or when they are in moves, a part of their brains as asleep, when they rest as awake. So chimera states have many variants. And one of these variants is traveling chimera state. And traveling chimera state for its part materialize the displacement of chimeral state in the time. On the basis of all this observation, we ask ourselves what would be the influence of electromagnetic fields on chimeral state in the neural network of type Hinman-Ross. And before answering this type of question, let us talk a little bit about neuron. As a scandal in 1991, he classified neurons according to their role and their position in the nervous system, and it classifies neurons according to their role, and we know that we know that we have a efferent neuron, which is also called a motor neuron, which transmit information from the central nervous system toward periphery, and afferent neuron, which is also called sensory neuron, which make the opposite action, so that it transmits information or nerves impulse from the periphery to the central nervous system. And we also have a interneuron, which has the role to establish many links between central afferent and efferent neurons. So we know that all neuronal cells have a common architecture, which consists to have a cell body and dendrite, axon, and many synapses. Neuron also have many mathematical models, and we are going into the case of this work to focus on the models of Hinman-Ross neurons. These models proposed by Hinman-Ross in 1984, and here we have X, which represent the potential of the membrane. Y represent the slow flow of ion, the high flow of ion, and Z represent the slow flow of ion. Once all these prerequisites is precise, let us now talk about the phenomenon appear in the one-dimensional neural network. Before, we are going to explain the configuration of the one-dimensional network we use in this work. So here, there is a ring of M elements, and the connectivity is illustrated as we can see in figure 2. Each element is linked to its two nearest neighbors with a local electrical coupling. Here we have it in black color, and to its two P nearest neighbor by non-local chemical coupling, which materializes here with a red color. This network is modelized by the equation 1, where G represent the electrical coupling, which we represent the electrical coupling, yes, and C, the chemical coupling. K1 and K2 are respectively the coupling coefficient of electrical and chemical coupling. In the chemical coupling is modelized by the sigmoidal function, where lambda represents the slope of the sigmoidal function, and theta represent the threshold of firing mode. Vs, Xs here represent the reverse potential. Now, when we implement this equation, we found some result which follows. By making a spatial-temporal evolution of the variable x here, we observe that for certain value of coupling parameter, the presence of pattern of the same color coexists with the one of multicolor. And these patterns are moving in the time. And for this reason, we subsume there the traveling chimera state, which is confirmed by the figure 3C, where we have plotted two waves of two elements taken in each time, of two elements taken in the ring. So we can see on this figure that there is a displacement between the waveform of element 5 and the waveform of element 15. And also, we can notice that all the nodes of the system behave with manifest irregular bursting. For another couple of coefficients, of electrical coefficient, we noted that the sense of traveling chimera have changed. So here, it's going from the bottom left to the top right. And the snapshot of two instants of all the elements of the network show us that there is a shift between the amplitude at the two moments. And here, we also know that each element of the network manifests a chaotic bursting. After setting this previous phenomenon, we are now going to deal with the influence of the number of the range which intervene in the coupling, with the chemical coupling. Here, what we note is what? We continue to observe the traveling chimera state for any value of P, of the parameter of P. P here is the range of coupling chemical, is the range of the chemical coupling. So it cannot be more than 49. And the only observation here is that when we change the value of electrical coupling, we observe the changing of the direction of traveling chimera only for the value P equal to. After observing this phenomenon, we wanted to have a quantitative idea of what's happened in the network. So we recorded the indices of element carry the maximum value in the ring at each instance. With these indices recorded like that, we are going to try to determine the velocity of the wave in the ring. For doing that, we made a time series analysis for this wave obtained by the maximum indices, and for them, we extract the fundamental frequency, which is the frequency of the wave form around the ring. And with this frequency, we were able to calculate the velocity of the wave, like showing on the formula 5. We observed that the velocity of the wave on the ring decreases when the electrical coefficient increase. After, we also continue to play with the electrical and chemical coupling. For a couple of these values, we observe that the appearance of two blocks of coherent motion in the ring. The coherent domain are in blue, and the others, which seems to be a little bit red, are not clearly a coherent domain, an incoherent domain. Here, we know that the block of incoherent domain are travel in the ring. And to be clear with that, we represent here the temporal evolution of the element of the node. And we notice that the zone, the white zone, which correspond to the blue domain, manifests the low frequency. And we also notice that when we decided to make a big size of this figure for some element, for a bit interval, we remark that all these domains appear regularly in the time, and because of this phenomenon, we name this because of this repetition, we name this phenomenon a traveling multicluster chimera state. When we modify the coupling function of this phenomenon, we also observe the appearance of 4 blocks of coherent motion. And for us to understand which type of behavior we have in this domain, these 4 blocks, we decided to name these 4 domains for the left to the right by 1, 2, 3, 4. And we observe that if we plot the waveform of each one element take in each of the 4 domains, we remark that the element of the first domain are not only coherent with the one element of the first domain are not only coherent with the element of first domain. He also coherent with the third block, and the same phenomenon is repeated with the second and the fourth block. So that we observe the antiphases in the representation of the waveform, and because we also observe the variation, the oscillation in time and space of the coherent domain, we name all these phenomena as traveling chimera breeders. For us to confirm that all the coherent domain we observe here with amplitude is also a coherent domain in phase, we call upon the notion of local order parameters. And with this expression given by formula 6, we were able to say if one element in the ring belongs to a coherent domain or not. And we see that when we evaluate this local order parameter on the ring, we observe that on all the previous domains which were coherent in amplitude, we also have a coherence in the phase. So we have the confirmation that we are on the coherent domain previously. Now we are going to check the existence of this phenomenon in the two-dimensional neural network. The diagram, the two-dimensional diagram, the connectivity is illustrated by the figure 10b, where the red node explains how each node of the network are connected. Here, the red nodes are locally connected to his 4 nearest neighbors by electrical connection, and non-locally connected to its P neural network on the left and on the right, on the top and up by chemical connection. The system of equation which helps us to modelize this system, this network, is given by system 7. Here, G and 6 IG represent the electrical coupling, and CIG represent the chemical coupling. P here also represent what we call the coupling, the chemical coupling range. When we implement this network or this equation, we observe that for a certain value of electrical and chemical coupling, it appears in the two-dimensional neural network some patterns which have the same color across the domain, and another which have multiple color. In the one which have the same color, they all have the same amplitude. So, by representing the block at two different times, we remark that all the block are not at the same position, do not keep the same position in the time. So, we were able to say that here we are facing the phenomenon of traveling chimera state. For us to confirm that it is the traveling chimera state, we plotted the two-dimensional snapshot of all the grid or all the network at two different instants. The red one is the last instant. And we can see that on this figure, there is a shift between the two waves in the two-dimensional network. So we will be sure that it is a traveling chimera state. For another couple of electrical coupling, we were able to see that the coherent domain doesn't have the same shape like the previous. Here, the shapes are not straight line like the previous, so they are degradated. And we also noted that all the elements of the domain manifest chaotic behavior, and there is also a traveling chimera state. One more thing is that here, the direction of the propagation has changed. For another couple of parameters, we see that the direction of propagation can change from a couple of coupling parameter to another. And because we observe this, we ask ourselves if there is not exist a kind of alternating traveling chimera. So we are going to verify in the time if this phenomenon exists. For another couple, we observe in two-dimensional neural networks the appearance of cluster. And we also see that these clusters are not fixed in the time, because here we can see that we have two interval domains, and the clusters are not in the same position, so that they are moving in the time. But the great difficulty here is to determine the direction of the propagation of the wave in the two-dimensional neural networks. So we decided to verify the existence of alternating traveling chimera state in the time. And what we observe is that by following here, we represent the figure at many times. And for us to follow the numerical times, you have to follow the red arrow. So you can see that when you went from time 3020 to 3350, you have the traveling chimera in one direction. Before reaching the time 6150, we pass through a transitional phase manifested by the two times, where we can see the degradation of the previous traveling chimera before reaching these times. And if we continue in figure 15, we can see that, in 15 or 16, we can see that after the previous traveling chimera state, we also see after some time a kind of transition manifested by these two figures, after which the direction of traveling chimera also changed. And at this level, we were not able to tell to determine the periodicity of changing because of the big number of our data. So here we notice the existence of alternating traveling chimera state in the two-dimensional neural network as we saw it in one-dimensional neural networks. Now, we ask ourselves, how can we determine the direction of traveling chimera state after observing all these phenomena? Before, we have to confirm that all the elements that we were saying they are on coherent domain are really in coherent domain. And for us to confirm, we introduce the two-dimensional neural networks, we introduce the two-dimensional local order parameters, which helps us to say if one element in the network belongs to a coherent domain. And what we face here is that all the previous states saying to be in coherent domains are really a coherent domain, because here they took the red, they all take the red color, which helps us to say that which is the representation of value 1. And we know that when local order parameter is 1, it means that we are all in the coherent or synchronized domain. After we want to determine the direction of the traveling chimera state, now we decided to determine the energy of all elements in the ring by using we decided to determine the energy of all elements in the ring by using the how do we call this? So we evaluate the instantaneous energy here of all elements on the ring, as shown in the figure 18A and 18B. So, by calculating the derivative of the energy for the element taking for the cross of our domain, we concentrate ourselves on the pattern of high energy, of high derivative energy. And with this energy, we were able to say that, to determine the direction of propagation of traveling chimera state. As example, for the case of figure 18C, we could say that the traveling wave going to the top right to the top right to the top right to the bottom left. And for this case, the traveling chimera going to the left right to the top left. Once you were able to determine the existence of all these phenomena in two-dimensional neural network, we come back to a one-dimensional neural network to study the influence of external electric and magnetic fields. So, at this level, we modelize our network by this equation based on the modified Hindman-Rose equation proposed by Mai all in 2019. Here, the external electrical field is given by this formula, formula 12. And let's remember one measure which will be very helpful at the end of our works. These measures are called strength of incoherence and discontinuity measures, introduced by Koppel in 2017. And for these two measures, we were able to determine if we have coherent state, multi-chimeral state, and incoherent state. We can see that for the two measures, taking the value 0, 0, we have a coherent state. Chimeral state means that the strength of incoherence is between 0 and 1, and multi-chimeral state, both of them, strength of incoherence are between 0 and 1, and discontinuity measure is between 2 and m over 2. M is the total number of the element in the network. The last value is for the incoherent ones. Now, when we implement this, we observe this result. For a low frequency, we observe the appearance of alternating traveling chimeral states as shown in the figure 19a. So, for us to confirm this phenomenon, we plotted the wave traces on figure 19b, and we can see that for two elements taken each in the two domains, we can observe the shift between the wave trace of each element. When we decided to increase the value of frequency of our external electric fields, we observed the appearance of traveling of chimeral state. And another observation we have done is that the element in a domain non-subjected to the electrical field manifests regular bursting, and the ones inside the inside the domain subjected to the electrical field manifest the dearth of bursting, After that, we decided to study the influence of the number of elements subjected to electrical fields. When the figure 20A and B is for the number of elements equal 75, and this is for the number of elements equal 25. And what we can observe here, what we can remark here is that for the number of elements subjected to electric fields equal to 25, we face that in a part non-subjected to electrical field, there is a manifestation of an imperfect traveling chimeral state, as you can see on the figure 20b. For us to make a generalization, we're varying the number of total elements subjected to electric field from 1 to 100. And the strength of incoherence and discontinuity measure help us to say that the chimeral states started to appear in the network for more than 20% of the total number of elements of element in the neural network. So, after that, we decided to apply the electrical field in two different domains for the same length. When we apply the electrical field for a couple of coupling coefficients, we observe the appearance of multi-traveling chimeral state, with the difference that in the part non-subjected to electrical field, we observe the alternating traveling chimeral state, and we still have in the part non-subjected to electrical field the dearth of bursting. And this state, which is confirmed by the figure 21b, where we represent the snapshot of all elements at an instant. So we name this phenomenon traveling multi-cluster multi-cluster chimera state. When we varying a coupling coefficient, we observe the appearance of multi-traveling chimera state because in the part not subjected to the electrical field, we also observe the traveling chimera state, and we baptize this phenomenon by traveling multi-cluster chimera state. And on this case, we also note that in the part non subjected to electrical field, each element manifests the chaotic bursting, and in the part subject to electrical field, element manifests a death of bursting. After that, we decided to study the influence of magnetic fields. The system of equation 16 helped us to modelize the network, and we follow the model proposed by Ma in 2016, where she represents the external magnetic fields. And when we implement this system, we observe the following results. For the previous state, we apply the magnetic field to the last 15 elements of the network. And what we observe is also the chimera state, but with the difference that in the part subjected to magnetic field, we are facing the oscillation of all elements in this domain. And in the other part, the element manifests regular bursting. This is proved by the figure 23b. And when we decided to apply the magnetic field for a couple of value of coupling coefficient at two different parts, we always observe the appearance of multi-cluster chimera state, where in the domain subject to the electrical field, we observe the oscillation of neuron in this domain. For another value of coupling coefficient, we also observe the multi-cluster traveling chimera state with the difference of this alternating with this oscillation in the domain subjected to the electrical field. So at this level, we ask ourselves what will be the mutual influence of the both type of fields, electrical and magnetic. We decided to apply the both to our networks. For us to implement this, we use the model proposed by Zhu and Wei in 2021, which take in account the both type of electric fields. And we decided that this both field could become from a waveform, and the link between the maximum amplitude of magnetic field and the maximum amplitude of electric field is given by the formula 19. So when we implement this system, we observe this result. As we set the previous parameters, we also observe in this case that when we apply the electromagnetic wave to the last 15 oscillators, we observe that in the domain subjected to electrical field, to electromagnetic field, elements behave by oscillating, and in the other domains they are in chaotic manner. When we decided to apply the electromagnetic field in two different domains, we also observe that in the domain subjected to electromagnetic field, we observe the oscillation of elements in the neural network. And We can conclude at this time that the effect of magnetic field is greater than the effect of electric field, because with electrical field, we were facing the death of bursting, and with magnetic field, we were facing the oscillation of element. So we can see here that with electromagnetic wave, we also facing in the domain subjected to the field the oscillation of elements. We represent here the summary of the three effects of the three case of figure. Here we have the application of external electric field only. Here we have the application of external magnetic fields only. And here we have the application of both. And we can see the difference. And we can see that with each of the field, we have different type of behavior. But when we apply the electromagnetic wave, it's like the magnetic field the effect of magnetic field is greater than the effect of electromagnetic field. And it is important to investigate what is going on at this for us to have this difference. As conclusion, we can say that we were able to highlight a variety of chimeral states in a ring of neural network only by modifying the external current and the coupling coefficients. We also checked the presence of all these phenomena in the two-dimensional neural network and highlighted the influence of electromagnetic fields on the phenomenon observed. So this work was done with this team, me, which is Simo, and Chirijugo, which is which is an Italy now, Raoul Aristide, which is in Spain, Lodo Patrick in German, Dibaka Ghosh in Indian, Robert Shidga in German also, and Ida Sedera, who is a professor here. This work gives birth to two papers you have here. And at this level, let me say thank you for your kind attention.
Okay, thank you very much, Gaël. Do we have questions?
Thank you, very nice talk. Let me see if I understand this correctly. You use it only regular networks.
Yes.
All right.
Yes.
Have you tried to use a complex network? Because I think the first patterns that you have showed to us in the beginning of the presentation, I think this effect occurs because of the regularity of the network. Don't you agree with this?
Yes.
All right. But it's only regular networks, yeah?
Mm-hmm.
It is on regular networks in this case?
I don't understand what your question. You asked me if this phenomenon appear only because we have irregular networks?
Yeah, this is the question. Have you ever tried to apply this in complex networks to see if you have the same result?
Yes, this also is a kind of complex network.
All right.
It's also a kind of complex network. You know, because you say regular because you can see we fix the position of each element in the ring or in the two-dimensional grid.
No, I'm saying that is regular because each node presents the same number of
the same number,
connections.
yes. And in a complex network, like you say,
like a random network.
Pardon?
Like a random network, for an example.
Even random networks could have a same probability of connections. So at this level, are you going to say that it's a regular network? No.
No, no.
So we are not investigate the case of random network or other networks for us to see if there exists the same phenomenon here.
All right.
Yes.
And I have another question. Why is the electrical field applied in the y variable, the second variable? The electric field.
The electric field is applied in the second variable. Yes. Here, when the author proposed the model, there is a relation between a fast current flow, fast current of ion through the membrane, and the external electric field, and the field that they create by moving, even in with a magnetic field or electrical field, because each ion through the cells, each charge can create in the nearest environment an electrical field, and if it is in moving, it can create magnetic field. The Laplace law. Yes. So the electrical field or magnetic field is coupled with the second variable because of these relations.
All right.
Yes.
Thank you.
You're welcome.
More questions over there? Okay.
I want to make a comment that I don't think we ever discussed anything like that. The point is, the magnetic field is nothing that is there because of the interactions between the networks. The neurons is something that you apply from outside. Let's say if you put someone under a trying to do a magnetic resonance or something like that. I mean, I need your imagination for what I'm going to say. So the point is, if you could focus, imagine that you could focus very well a magnetic resonator so that you would know exactly which place of the hair you apply the field. Although the magnetic field, you know pretty well that you cannot apply it exactly the place. But anyway, as I say, a lot of imagination. So the point is, imagine that we could do that experiment. So would this, I'm not even saying would the chimeras, but would this alternate movement of different states that you see in the last figures?
Yes.
Do you think that you will see something like that in a magnetic, in an MRI?
In an
MRI? Because if something like that would exist, an MRI, it will be more difficult to interpret than what it is right now. No, I mean, you don't need to answer.
Okay,
I'm just
okay.
throwing a crazy idea. So, no,
Okay.
I don't know what will happen, because that will say, I mean, if all this could be done really, in real life, I mean, and this alternative, can you put the last figure?
Yes.
I'll tell you which I'm talking about.
The last figure.
The last, in which you showed all the states together. That one, yeah. Take a look at the ones on the right. Take a look at that on the right, and take the cleanest, the last figure on the right,
Yes,
the one
one
below. So you see that even when you don't have the chimeras, when you don't have the disorder, let's say, the chimera is the whole thing. If you don't have the disorder, you see that you have states that alternate. They are synchronized, but they alternate. The first and the third are like that, synchronized and alternate. What I'm trying to say is if this thing will happen in real life, an MRI, a real MRI will be, I mean, will either appear blurred, or it will depend exactly on the time in which you take it. because these things, because I'm trying to say if you could make you could do an experiment of magnetic resonance in which you could really pinpoint to where you put the magnetic field. That's something that's very difficult to do. So, I mean, I don't know if we would see something like that if it will not change the whole technology of the, I mean, because it had to be thought again, how to interpret. So that's what I'm, but forget about this, just one of those.
Okay.
More questions? Okay, there.
Thank you for your presentation. Could you put on slide 14, please?
Slide 14.
Yeah. You mentioned when you model the two-dimensional one.
Yes.
14.
14.
I don't know if yeah.
This one?
No, 14, like 1-4.
Ah, okay, 14. Excuse me.
The one below. Yeah. This one.
Yes.
You mentioned that the chemical coupling is added only to the ones that are further neighbors up, down, and to both sides, right?
Yes.
Why did you choose to do the chemical coupling only in the axis and not in a radius or some other type of chemical coupling in 2 dimensions? Do you understand my question?
Yes. We wanted to implement the non-local coupling.
Okay.
Yes.
A simple one.
Simple one.
Okay.
Yes.
Have you tried with
And,
any other type of non-local coupling, but not this one on 2 dimensions?
This one on 2 dimension because we remarked that it is a little bit near to what we have in the lamel of real neural network in the reality. And you can see that here we have many chemical coupling than electrical coupling because in the reality we also have many chemical coupling.
In the membrane, you mean?
Yes.
Okay.
And what we try to do here is to check to have to find which kind of network can behave or can manifest a real phenomenon we saw in certain animal, like traveling chimera state or like chimera state. And by checking it, we find that this type of network can behave like that. So by implementing this type of network, we were able to have a beginning of answer for the appearance of this type of phenomenon.
Okay, yeah, thank you.
Thank you, too.
But also complementing related to that, maybe
Yes.
related to the first question. I don't know if it's just the impression, but it looks like as you're choosing axis, maybe the traveling behavior is because of this structure of how you're choosing the non-local
No,
couplings. But I don't know if I'm looking too much forward.
I think it's because we choose a non-local coupling. Thank you. Thanks.
We have time for more questions. More questions? I have a question. So,
Yes.
it's on slide 19.
Slide 19. Yes.
The next one.
The next one. This slide.
Yes, where we have the alternating traveling chimeras. Do you have an index to say, okay, here we have alternating traveling chimeras. Can you detect, by using a measurement, if you have an alternating chimeras or not, instead of just using the visualization?
Okay, thank you. So here we have for this simulation, we have more than 10,000 instances of data. So at each instant, we have also 10,000 data to collect for the two-dimensional graph, because you can see here it's a 100 times 100 element we took in the rod. So we have 10,000 element here.
Okay.
And for this 10,000 element, we also record 10,000 time of simulation.
I see.
So it was difficult for us to represent all the data at the same time and to try to measure it.
Mm-hmm.
We are now discussing on a method to detect the traveling camera set, because on our knowledge, it doesn't exist for the moment.
Okay.
If we have the method to determine the existence of traveling camera state and detect the existence of traveling camera state, we were able to apply it on all our data and saying if after which times the phenomenon appears or change the directions. Yes, so
Okay.
we were not able to determine exactly the time.
Oh, I
We
see.
just cut. We just take the time randomly, the interval of time randomly, and observe what appear. And this, yes.
Okay. Thank you.
Thank you too.
So we have 3 more minutes. Do we have more questions? If not, we are free for the coffee break. Thank you very much. Let's thank Gaël again. Thank you.
Thank you.